This video is in response to two questions that I received. The first was, how do I calculate the size of a protein on an SDS-PAGE gel? And the second question was, can I use the DNA method for proteins? Well, if you've watched my video on how to calculate the size of a DNA band on a gel, you'll know that if you have a DNA gel that looks like this with the DNA ladder down one side with the sizes in base pairs, you can calculate the size of an unknown band. And the approach that you take is you construct a table with your base pair sizes in it, and then you work out the log values for those base pair sizes. The next thing you do is measure the distance that the bands have moved in lane 1. In this case, the first band has moved 22 millimeters from the center of the well, and you repeat that for all the bands including the unknown. You then use that data to plot a graph, and you can then work out the size of your unknown band. The approach we use for proteins is pretty much the same. So after you've run your protein SDS-PAGE gel, you'll have something that looks like this. The first thing that you'll note is you can't see any bands on it at all apart from this blue line at the bottom, and this is the dye front. This is the dye that was in the sample buffer that was used to load the proteins on the gel. Sometimes you might be able to see the proteins in the protein molecular weight ladder because they've been pre-labeled with a dye. And in that case, your gel may look something like this. You will know from the manufacturer the size in kilodaltons of each band, and here we're running from 250 kilodaltons down to 15. And this example is using a 10% gel. So that means we've got 10% acrylamide in this particular gel. Then after staining, which could be any number of stains, but in this example we're using Kamasi stain, you would get your bands appearing in the other lanes. Normally you would see multiple bands, and just to make things easier here, I'm just showing the one band, the unknown band that we wish to calculate the size of. As we did with the DNA gel, we construct a table. We put in the sizes in kilodaltons of our proteins in the protein molecular weight ladder, and we work out their log values. And again, we measure the distance that the bands have travelled from the centre of the well. So the first band has moved 15 millimeters, so we write that in the table. The next band has moved 38 millimeters, so we write that in the table. And we repeat this process for the other bands. We also measure the distance travelled by the unknown band, which is in this case 78 millimeters from the centre of the well in lane 2. Finally, what we need to do is measure the distance travelled by the dye front, which is 153 millimeters, and again we can record that. Now, one thing that we do that is different with the protein gel is we calculate something called the RF value, and we construct a column in the table for our RF value. Now, what RF stands for is retention factor, and this is a measure of how far something has moved in the gel compared to the dye front. So we know how far our bands have moved. So for example, for the 250 kilodalton band, we know it's moved 15 millimeters. We know the dye front has moved 153 millimeters. So to work out the RF value, what we do is we take 15 divided by 153, and that gives us 0.098, which we put in the table. We repeat this process for all the other bands. So for example, the 150 kilodalton band has moved 38 millimeters, so 38 divided by 153 gives us a value of 0.248. And we just repeat that process for the other bands. This is more of a traditional thing that we would do with protein gels, and we don't have to do it. We could have just plotted the distance, but we tend to use these retention factors, these RF factors. And finally, we calculate the retention factor of our unknown, which in this case is 0.510. The reason we use retention factors is because we get day-to-day variations in the way the gels run. However, the retention factor should remain the same in different gels, so it enables us to identify the same band on different gels. Once we've completed the table, the next thing we can do is plot our graph. So here is our graph. From the table, I know that I need a range of 1 to 2.4 logs for the kilodaltons and an RF value going from 0 to 1 up the side. I plot on my data, and then I can calculate some key components for this graph. I can determine the gradient m, the intercept c, and also the fit. Here I've got a very good fit of 0.9991. Normally when we do these graphs we end up with a slight curve. We end up with the two extremes with the point slightly above the line. But here in this set of data we've got a very good fit indeed. Our unknown is at 78 millimeters, which as we know is a retention factor of 0.510, and then we can plot this value on the graph. We find 0.510, we draw a line across, and then we drop a line down from the intercept from the graph line, and that gives us a final value of 1.764. We can also calculate this value using y equals mx plus c, using the values that we've got for m and c in the table. And this gives us a log value of 1.7644, and from that, if we anti-log that, it tells us that our unknown has a molecular weight of 58 kilodaltons. So that is how you determine the molecular weight of a protein on a gel. You plot the data using the RF values and the log of the molecular weight, and then you can determine, based on how far your unknown has run, its size in terms of kilodaltons. So in summary, this method only works on fixed percentage gels, for example a 10% gel. The method does not work on gradient gels where you've got an acrylamide gradient going from, let's say, 10 to 20%. It won't work there. And also it will not work on what we call native gels, where there's no SDS present to denature the protein. And you should note this method is not very accurate. It's an approximation, so please don't view this as being the final molecular weight for a given protein. You really need to get the sequence and to work it out. Also, certain modifications of the protein that occur in the cell can change its apparent molecular weight on an SDS-PAGE gel. If you want more information on how to do the analysis for a DNA gel, then you might want to watch the video that's showing here now, or if you want help drawing a graph, I've also got an excellent graph drawing video. Thanks for your time and good luck with your gels.